Hello, lovely humans, Jen foxbot here. In today's Math Mondays episode, we are going to dive into line integrals. Ooh, yeah! So, if you are a physics student, or if you have another major where you have to learn physics, surprise, physics is all around us and it's very useful for lots of different things, then you might have come across a line integral. They're really common in physics because they're super useful. Basically what it is a tool for us to sum up contributions of something over a given path. So it's kind of like we're sweeping up a bunch of stuff along a prescribed path. And so typically the path that you take to sweep up these things is going to change what you're sweeping up or how much of the stuff you're sweeping up. But sometimes if you come across something called a conservative force, it doesn't matter which path you take because you will get the same result. But to show you how oftentimes the path that we are taking matters, both in life and in math, we're going to do an example of a line integral that does have a different outcome depending on which path you take. So you're like, well, what the heck are you talking about? Let's look at some math. Okay, so the equation for a line integral is like this. You take the integral from point A to point B, from point 0 to point infinity. So from point A to point B, where you have some vector, which is just an equation describing the shape of something, and you take the dot product with the displacement infinitesimal vector. And basically what this means is, let's say you have some shape here where this is V, and this is A, this is B. Your displacement vector is going along, and the dot product is the projection of V onto this teeny tiny dl. Basically your infinitesimal displacement. So if you were to figure out the distance between, well, okay, I'll just leave it there. Okay, so just really quick to show you what the dot product means. If this is V, oops, let me make it a little bit more realistic. If that's V and this is dl, the dot product is the projection of V onto dl. And so V dot dl would be V times, I should say, V times dl times the angle between them. Okay, I lost my eraser, so I grab it. Okay, I hope that helps to clarify a little bit. Basically, you can think about it like we are finding the amount of V that is in this direction dl. Okay. So if we have a closed path, you will see something like this, where the circle is just like, hey, we are ending up where we started. So this is A and this is A, and we are coming all the way back around. So that would be like if we were to come back here. Okay, cool. So now that we have clarified what the general equation is, let's actually apply this, because per usual, it's a lot different just talking about it than it is actually using it. So, okay, let's say that we have a vector V that is described by the equation y squared x hat. I think that's right. Hold on, let me check my notes. Be bad to get the actual example wrong. Okay, yeah, plus 2x times y plus 1 y hat. And we are going from point A equals 1, 1, 0 to B equals 2, 2, 0. All right, so it's nice because this is only in 2 dimensions instead of 3. It makes our lives a little bit easier. So that would basically be like, if this is y and this is x, this is our point A at 1, 1. This is our point B, I should label that, at 2, 2. And we are going to take this approach in 2 ways. So we are going to go the scenic route and go in the horizontal x direction first, and then up in the vertical direction. So this is going to be path 1. This is part I and this is part double I. I would use A and B, but I've already used those. Oops, that's okay. And then we'll take the path in the direct route, like, all right, we're gonna parkour our way through from A to B. And so this is our path number 2. Okay, so for path 1, it's also really helpful to note that the vector DL can be basically written in terms of X, Y, and Z. I might not have enough space up there. So we will do that here. So DL equals dx x hat, where x hat is just a unit vector in the y direction, basically length 1. It just tells you where to go. And in this case, it's like, go in the x direction, go this way, plus a tiny chunk dy in the y direction. And this one is like, go in the y direction, plus, since we live in a 3-dimensional world, dz z hat, but in this case, this is going to go to 0. We're only looking at 2 dimensions. Okay, so the first thing for us to do is to figure out how dl changes on each of these paths, because dl is a vector. This is going to, its direction is going to change depending on where we are in the path. So this first path is kind of nice because for each direction, for this first horizontal direction and for the vertical direction, in the horizontal case, we're only moving in the x direction. And so in that case, dy is 0. It doesn't change. Boom! So that makes our lives a little bit easier. So then in this case, when we do v dot dl and we multiply the components of v with the components of dl, we get the x hat pieces multiplied together to give us y squared times dx. And just note that a unit vector times itself is going to equal 1. And in this case, the dy pieces go to 0, so that's all we have. Oh, hey, by the way, y is constant. And in fact, it equals 1 along this whole path. So y equals 1. We can plug that in here and then get v dot dl is just equal to dx, because 1 squared is just 1. Boom. Oh, look at that. And so now all of a sudden, the first part of our path from x equals 1 to x equals 2 is just the integral of dx, which is going to give us x from 1 to 2. 2 minus 1 is 1. Not so bad. Okay, so now let's do the vertical path. This was I, and then this is going to be double I. Woohoo! Okay, so then in this case, dx is 0 because x is constant along this whole way. Oh, and by the way, x equals 2 along this path. And so our vector v dot dl, in this case, dx is 0, so only the y components get pulled out of the dot product. So we get 2x times y plus 1 times dy. And so x equals 2 in this case. So, oh, boom, we plug in a 2 here. 2 times 2 is 4. Oh, yeah, look at that. Not so bad. Okay, then we plug it in to the integral in the y direction. We're going up now from 1 to 2. Forgot to label that. From 1 to 2 of 4 times, whoopsies, not x, my bad, 4 times y plus 1. I know, Marley is like, oh, you made a math error. 4 times y plus 1 dy is going to give me 4 times 1 half y squared plus y from 1 to 2. I can bring in the 4, simplify this a little bit. We get 2 squared plus 4y from 2 final minus initial. So this is going to give me 2 times 4 plus 4 times 2 minus 2 times 1 plus 4 times 1. So this is going to give me 6. This is going to give me 16. And so we get 16 minus 6 equals 10. Boom. Okay, almost done. So now we have to add these two together. So path 1 plus path 2 equals 1 plus 10 equals 11. Boom. Okay, so since this isn't a physics problem, we don't have units. Woohoo! We didn't drop anything. Okay, so that is our first path. Boom. Done. No problem. Now, let's see what happens when we take a different path, the direct route, the straight line approach. So, I want to save this. So path 1, we'll say path 1 equals 11. And then we will erase this to give ourselves more space. Okay, so what I like about the first path is that it allows us to take a bunch of things and set them equal to 0. So we're only dealing with one direction at a time. In the first part of the path, we're only dealing with x changing. In the second part of the path, we're only dealing with y changing. Cool. All the other variables go to 0. In this path, both x and y are changing at the same time, but they are related. They depend on each other, you could say, and you can write x in terms of y. So that's the first thing that we have to do, is recognize we don't really want to deal with two variables at the same time. And so how can we rewrite the second path so that we only have one variable? Well, interestingly enough, this path from A to B along this diagonal route is of the equation y equals x. Look at that. And so that also tells us that dy equals dx. Boom! Our magic equation, which allows us to replace all of which allows us to rewrite v in terms of one variable. I'm going to pick x just for funsies, and so in this case we'll get v equals x squared x hat plus 2x times x plus 1. And now we can do dl dot v, or sorry, my bad, that's very different, v dot dl, which equals x times the x components multiplied together give us x squared dx plus 2x x plus 1 with dy, so y components times the y components. But we already said that dy equals dx. So boom, we can change that to dx. Well, not change it, equate it. Woohoo! Okay, so now look at that. Even though both x and y are changing, and it seems a little bit trickier, we have used our math powers to get rid of all of the y's and replace them with x's, and it is all still equivalent. We have stayed true to the rules. So now we can do the path, and since we are only working in terms of x, we're going from 1 to 2. I guess it would be the same for y, but so it goes. And so then we plug in this formula. I guess I can simplify this. So we're going to get 2x squared plus 2x. So this is going to give me 3x squared plus 3x cubed. Wait, no, that's silly. 3x squared plus 2x. And then all of that times dx. And we take the integral. And oh, look at that. The 3 cancels. We just get x cubed. And the 2 cancels, x squared from 1 to 2. And so then 2 cubed is 8 plus 4 minus 1 plus 1. 8 plus 4 is 12 minus 2 is 10. Boom! Oh, like a boss. Hey. Okay, math boss. Okay, so in this case, the result of our path is 10. And again, there's no units, but I mean, 11 is bigger than 10. So in absolute numbers, we can say that it was shorter to go from A to B along path 2. A little bit more of a direct route. And in physics, this would, have certain units to it. Maybe in this case, it was there was more work required to go from A to B in this way, which makes intuitive sense. Cool. Okay, so I hope that helped to clarify and or teach you how to do a line integral. Of course, I picked a simple example. Things can get complicated really quick, and I always get annoyed with my professors. It's like, you do the simplest example in class, and then you give us the hard problems on your homework. Yes. But if you have any questions about line integral problems, I am happy to help you work through them. I will not do your homework for you, but I will help point you to resources. And if you have a specific question, aka you know where you're stuck and why, please reach out and let me know, and I'm happy to help you work through it together. Also, let me know if you have any questions about other math topics. I'm going to be using this to launch into a series about electromagnetic theory, which is also called electrodynamics. Fun! It's called electrodynamics because electricity moves. Oh yeah! Cool. So that should be a lot of fun. But of course, any other topics, ping me and I'll add it to the queue. All right. Thanks very much for watching, and we'll see you next time. Bye!